Good afternoon or good evening, dear student or dear viewer, depending on the time at which you'll be watching this video. Welcome to this other series of our mathematical knowledge class. Today we are going to cover a Trigonometry Refresher series. Why Trigonometry Refresher? Trigonometry plays an important role in mathematics and in applied mathematics, sciences, engineering, because in trigonometry we study triangles and the measure of the angles of those triangles. Trigonometry dates many thousands of years, that is millennia ago, since ancient Egyptians, or who are also called Kemites, in the tomb of the pharaohs and also on the papyrus writing, you will find trigonometry. The famous theorem known as Pythagoras theorem are found in the pharaoh's tombs, and this knowledge was known by the Egyptians thousands of years before Pythagoras. So that theorem can also be called, in memories of ancient Egyptian, Kemites theorem. But that's the issue here. It's also good to recall historical facts in order to honor those to whom honor is due. Okay, usually in trigonometry, there is an important aspect, which is the unit circle. We will introduce the unit circle, and we use the unit circle to derive most of the trigonometric identities that are being used throughout mathematics nowadays. So without any further ado, let us start our study with a definition of what is a right angle, and we also define sine, cosine, and tangent, which are also known to the anacronyms SO, CATOA. So for the definition of the sine of an angle, Ca for the definition of the cosine of an angle, 2R for the definition of the tangent of an angle. First of all, let us start with this this figure here. We have a triangle with 3 sides and 3 corners. We call this triangle ABC in the counterclockwise direction. We have the right angle, which is denoted or referenced here by a small square. Opposite this is what we call the hypotenuse, and opposite our angle theta is what we call the opposite side, and one of the legs, that is the side AB, is adjacent to theta. That is the adjacent side of the angle. So sine through so we have O and H. O is for opposite and H is for hypotenuse. So sine of an angle is defined, of course, when you are in a right triangle, is defined as opposite of a hypotenuse, and cosine of the angle theta is defined as adjacent by hypotenuse, and 2R, that is the tangent of an angle theta, is defined to be the opposite for O and adjacent for A. Now, back to our circle. If you draw a circle in a plane, a reference by the referential or the axis XY, if you take a point M in the space, a point lying on the circle, we can identify the position of the point M by this x and y component. So if we project the point M on the x-axis parallel to the y-axis, that is an orthogonal projection, we have the component x, and on the y-axis we project, we get exactly the component y, the y component of the point M. So using the fact that we can construct an angle to the point O, x and M, we have a right angle, a right triangle, because we use the orthogonal projection. So OXN forms a right triangle, and we can apply the definition of the sine, cosine, and tangent for this given angle, theta. So, using Pythagoras theorem, since our angle is a right angle, our triangle, the so-formed triangle is a right triangle, so we can use Pythagoras theorem or Kemites theorem, and then we read the adjacent side. If we square it and we add the square of the opposite side, it will be equal to the square of the hypotenuse. But since the adjacent side measures x, therefore our formula will give us x squared plus the side, the opposite side is y, it will be plus y squared, and the opposite, the hypotenuse side, measure r, is the radius of our circle, r squared, and since r is equal to 1, we equate it to 1. Okay, so using the similar definition of the cosine and sine of the angle, we have sine of the angle theta is opposite, that is y by hypotenuse, which is r. So sine theta is y by r equal to 1, so sine theta is y. Similarly, cosine theta will be x by r, which is x because r is 1. Therefore, we have the value of x, which is cosine theta, and the value of y, which is sine theta. So if we substitute these two values of x and y into this formula, x squared plus y squared equal to 1, we obtain the first formula, cosine squared theta plus sine squared theta equal to 1. So that is the first formula, and from this formula we can derive many other formula, but we are going to do that later. But at this stage, we need to know how can we derive the formula, the famous formulas, the sine of the sum of two angles a plus b, and cosine of the sum of two angles a and b. Actually, a and b were supposed to be replaced by cosine, theta 1 and b theta 2, right? Just because of notation, because it can be confusing. You might think of a to be a distance or measure, but everything will be based on the concept. So I mean on the particular concept. Okay, so how do we derive such a formula? Because in most of the trigonometric textbook or calculus textbook, we just see the formula, but we don't know where they come from. Or if you ask a student to prove the formula or to derive the formula, you will not be able to do that. You will just recite it. So now we are going to use a concept from linear algebra, the rotation matrix. A rotation matrix for an angle in the anti-clock direction, which is a positive direction, an angle theta. So the rotation matrix is given by the following definition. So r theta, which is a rotation of an angle theta, is given by the following 2x2 matrix. The first column reads cosine theta, sine theta, and the second column negative sine theta, cosine theta. That is when our rotation is anti-clockwise. And we can compute the determinant of this by taking the cross like that. Cosine times cosine, that is cosine squared theta, minus sine theta into negative sine theta, it gives us plus sine squared theta. We know that cosine squared theta plus sine squared theta is equal to 1 from this. So this is the determinant of a rotation matrix. It is positive 1. But for a symmetry it will be negative 1. But that's not the concern of today. Now, if we perform two rotations, let's say, for instance, we want to rotate the point N to its image N prime by performing a rotation from N to N prime. So this angle from the axis, the x-axis, to the axis through, or the line through ON prime, this angle is theta 1 plus theta 2. It is given here in red. But we can reach here by two rotations. We can first rotate from N to a second point here that I will call A. Right, this point, I can call that point A. So I can perform this first rotation, I will call it theta 1. And then I can rotate from A to N prime, and that rotation will be a rotation of angle theta 2. So you can see that we can rotate the point N1, the point N to N prime by two rotations. The first rotation is by an angle theta 1, and the second rotation by an angle theta 2. So you can see that this double rotation is the same as the single rotation theta 1 plus theta 2. So that's why we can write here that rotation of the angle theta 1 plus theta 2, that is a single rotation, is the same as performing a first rotation from theta 1, first rotation by theta 1, that is r theta 1, and then we perform a second rotation from that first rotation. That is, once we reach here, we carry from the support of theta 1 another rotation by an angle of theta 2. So we will apply the second rotation by the angle theta 2 to the result obtained by the rotation by the angle theta 1. So this is a matrix, it's a product of two matrices that give us that rotation. It's a composition. So we can write the matrix of the angle theta 1 plus theta 2 using this definition. We substitute theta with theta 1 plus theta 2. We obtain this corresponding matrix here. And that will be equal to the product of these two matrices. The first rotation, which is r theta 1, is given here. We substitute theta 1 here, so we obtain cosine theta 1, sine theta 1, negative sine theta 1, cosine theta 1. And the second rotation is by the angle theta 2. So we copy exactly the same thing here, but we change theta 1 into theta 2. So the next thing to do is to perform this matrix multiplication. So for the first entry, here, this entry is denoted by first row, first column. So first row, first column is performed by taking the first row of the right-hand side of the left-hand side matrix, multiplied by the column or the first column of the right-hand side matrix. So let's say this is what we are performing. This times that. So it gives us cosine theta 2 into cosine theta 1, which we can see, right? Cosine theta 1 cosine theta 2 minus sine theta 2, sine theta 1, or sine theta 1, sine theta 2, which is given here. So that is for the first entry. Now for the second entry, we are seeing in the first column. So we keep this one and we use this second row. So this is a second row, first column, second row, first column. So if we perform, we have cosine theta 1 times sine theta 2, cosine theta 1, sine theta 2, plus cosine theta 1, cosine, plus, because I multiply this with that one, and then we have plus sine theta 1, cosine theta 2, which is given by this. So that is it for the first column. Now for the second column, this position is in the first row, second column. So first row, second column, which will be this one. You see that we have already this negative. So we have negative sine negative here, yes. We have negative sine theta 1 cosine theta 2. That's negative sine theta 1 cosine theta 2, which is here already. And then we have the negative sine theta 2 cosine theta 1, which is this one. Negative. So we have negative, which you can factor. So cosine theta 1 is this one and sine theta 2 is that one. We just rearrange. So you can see that it's negative this one. And for the last entry, it will be exactly similar to the first one. Now, since these two matrices are equal, we can equate the like entries. So in other words, we will have, to make the thing fast, I will just copy this. So this entry will be equal so that entry will be equal to what? This entry will be equal to this other entry. So we can also copy this. So they will be equal. So that is for the cosine. And now for the sine, this entry will be equal to this other one. So we equate the corresponding entry. So we have sine theta 1 plus theta 2, which will be equal to the corresponding entry which will be equal to this corresponding entry here. So that is it. So we have cosine theta 1 plus theta 2. It is cosine theta 1 times cosine theta 2 minus sine theta 1 sine theta 2. And now for the sine, we have sine theta 1 plus theta 2 will be equal to cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. Now for the cosine, you can see that when we have plus here, it's negative to here, and when it is for the cosine, for the sine, we have plus plus. So that is how you obtain the formula. Now, we can easily do the same if you have negative here, negative there. We just use the fact that we replace, let me quickly show that. But here, we can do exactly the same thing. We can repeat with a negative and do exactly similarly. But we can use the result knowing that cosine and sine are odd and even though we have not proved it yet, but we can use that same information to obtain the other formula. So how do we do that? If you want, for instance, to compute the cosine, sorry, if you want to compute the cosine, let's say A minus B, we can write that to be cosine A plus negative B. Now this will be our theta 1 and this will be our theta 2. So we just go into this formula, we replace theta 1 with negative B, but since cosine is an even function, we will absorb the negative sign. But when we replace here, sine is an odd function, so the negative sign will be, returned here, so we have negative will be positive. So that's why negative here will become positive. So it is easy to do that and say it that way. Okay, so at this stage we will look this and we can quickly derive other formula. For instance, we can derive other formula. Let's say, for instance, so we have this first formula. Now we have two extra formulas here. We have 2 and 3. We have this one, 2, and we have also this other formula, 3. So we have this 2. We have 3 formulas in total. So what do we need now? We can compute double angle, for instance. Double angle. So if you want to compute double angle, let us copy this and move to the next slide. If you want to copy, so let's move to the next slide. Next page after. Okay, we can paste that. Good. So these are the two. Now if you want to define double angle formula, so let us write here double angle. Angle or angles. Okay, so if you just take theta 1 equal to theta 2 equal to theta, so let theta 1 equal to theta 2 equal to theta, and we can use 2 and 3. So if we substitute that into 2, we obtain the following. So we can say here that 2 become cosine 2 theta, cosine 2 theta will become what? Theta 1 is equal to theta 2, so it will be cosine theta, which is cosine squared theta, and similarly here minus sine squared theta. And similarly for sine 2 theta. So if we substitute here, we have cosine theta, sine theta, cosine theta, which is exactly the same. Because sine theta, cosine theta is still cosine theta, sine theta, which is already cosine theta. So this will become 2 cosine theta, sine theta. or sine theta, cosine theta. It doesn't matter. The order does not matter. So we have already this new formula. This is 4 and this is 5. So now you can see that from this we can obtain a form of linearization. Let's say if we have sine square or cosine square, we can compute cosine square or sine square in terms of a linear cosine. Okay, let's do that. Okay, so this 4, if we substitute cosine using formula 1, so cosine square from 1, from 1 we know that we can write cosine square theta to be 1 minus sine square theta, right? So if we use this and substitute into 4, so this, let's say, implies if you substitute it into 4, I don't want to number this. If you substitute there, we get cosine 2 theta is equal to 1. So if I substitute this here, you see that minus sine square theta minus sine square theta, so this will be 1 minus 2 sine square theta. And in the same formula, still from 1, we can write that sine square theta is equal to 1 minus cosine square theta. Now if we take this and substitute there, we have negative here, negative 1 and plus. And we add there will be 2 cosine square theta minus. So if we substitute that into 4, we get cosine 2 theta is equal to 2 cosine square theta minus 1. So you see that we are already generating a lot of formulas. So this is 6, this other one is 7. So we can box all these. We can box them. We have this, we have that. We also have, okay, those two. Let's box here, this one. So we have a lot of formula already that we generated. Just from what? From the first, from this fundamental relation that comes from Pythagoras theorem or Kemites theorem. And we use the composition of two rotations to obtain the cosine of the sum of two angles, similarly for the sine of the sum of the different two angles. And from there, from this, we can get a two angle, or this formula from two angle. We can even get for three angle, four angle. Now, if we want for three angle, we'll just write and we'll still use formula 2 and 3. Let's say, for instance, if I want cosine, sorry, if I want to find cosine, if I want to compute the cosine of 3 theta, we can write that as cosine 2 theta plus theta, and we use equation 2. We just use equation 2 and substitute. So what is that? So this will be cosine of what? 2 theta cosine theta minus sine 2 theta sine theta. But we know already what these correspond to. We know what cosine 2 theta corresponds to. We can replace this one by those. So, and also this one for sine 2 theta, we can replace that. But for cosine, we have three formulae, but they are all powers of cosine. So it's up to us to decide if we want to write just in terms of okay, so for this one, since theta is present already, we are going to use for this one the formula using equation 7 would be better, because we already have a cosine square here. So if we substitute that, we have we can write here, this is 2 cosine square theta minus 1 into cosine theta, and then this one for the sine 2 theta, we only have one formula, so we can substitute that. That will be minus this expression, this one into sine theta. So if I multiply sine of 2 theta by sine theta, so here I will get 2 cosine theta sine square, sine square theta. So if you want to express everything in terms of cosine only, I can also use this this formula, substitute it, and express everything in terms of sine square theta. In terms of cosine square theta. Okay, so let's expand this. So this one will give us 2 cosine cube theta minus cosine theta, like this. And now this one minus 2 cosine theta into 1 minus cosine square theta, so which gives us 2 cosine cube theta. We have another cube here, so plus 2 cosine cube theta, so we have this one and this one expanded, give us this 2. Now the remaining, we have negative cosine theta, negative 2 cosine theta, that will be negative 3 cosine theta. Now we can group finally and say this is 4 cosine cube theta minus 3 cosine theta. Right. So this is how we can write cosine of 3 theta. So we can do that for any angle. You can just use those for any angle, but you can also use something to do that. Okay, let's call this 8, equation 8, and let's box it. Right, so this same formula can be used. We can derive the same formula by what we call Euler's or de Moivre, what some call the Moivre formula. That is, we can use Euler's formula from still trigonometry, obviously I'll be skipping something. I will just use it. I will use that directly. Euler's formula. Which is also the formula or identity, which is obviously is a polar form of complex number, so I would assume that we know what a complex number is. So a complex number written in this form, you can write that in polar form to be r exponential I theta. But in our case, if we are using our trigonometric circle, you can assume that this r is 1. So Euler's formula, or the novel formula, tells us that if I raise this to a certain power, that is, if I raise z to the power of n, which is the same as I n theta, it is the same as if we write this so these two are equal, and you can see that actually Euler's formula that I was talking about is given by this. So the Euler's formula, let me write that in red, it will give us this one. So we have exponential I alpha being an angle of theta, this is equal to cosine theta plus I sine alpha. So now if I take this, if you assume that r is equal to 1, if you assume that r is equal to 1, taking r equal to 1, we have, so if we write this expression, this, which I can denote, let's call that star. So star will be equivalent to r equal to 1, so we write this, so it will be equivalent to what? I n theta. So we have cosine n theta plus I sine n theta is equal to this expression. Now, what is x? If you recall the expression of x, we saw that x is cosine theta, and y is sine theta. So we can expand this using the binomial expansion. Let's do it for 2 and 3. Let's do that for 2 and 3 and see what we get. You can do that for any angle. That's just to show you that instead of expanding all this for large angle, you can just use this result, the Euler's formula. You can use that. You can use this formula with the binomial expansion. Obviously, you use a Pascal triangle to do that. For the Pascal triangle, that's to get, of course, Pascal triangle will allow us to get the coefficient if you don't want to use a binomial coefficient, right? You can quickly do that for a few. Of course, to do that, it depends on, you can do this 1, and then 1, 1, and then you do 1, you say 1 plus 1 is 2, like this, and then you add 1 at the end, and you come here, you add another 1. The next will be the sum of the one above and the previous. You can see that here there's nothing. It's 0 here. If you add to that, it's 1. Above here 0, you add to that, you have 1. Right. So each one in the column here, the above is 1, the previous is 0, so it's 1. So now, this plus that is 3, 2 plus 1, 3, here's 0, so 1 plus 0, 1. You can, anyway, you can do that. So this is the exponent. This exponent, this is 0. Okay, let me write the exponent in red. So this is 0, this is 1, this is 2, this is 3. That is n, the exponent in the expansion. So you'll be able to read the binomial coefficient from here. So let us quickly do for 3. We don't have enough time. We'll stop very soon. So if we use this, n equal to 3 will give us cosine 3 theta plus I sine 3 theta. This will be equal to what? Then we use this binomial expansion. Okay, binomial expansion, first of all, we are going to perform a certain combination. First of all, let us expand this. Okay, let us write it. This will be cosine theta plus I sine theta to the 3. So we know already we can leave the binomial coefficient, but let us write the various combination here. So we start from cosine cube theta, that is this one cube, and then the power of this will be to the power of 0. So we start 3, 0, and we take the possible combination. So the other factor will be to the 0, which is 1. Then what is plus or minus, we leave the blank there. And then the next will be, we reduce this power and increase the power of the second term. So if we decrease, we have cosine square theta, and this will be I, because it will be to the power of 1, so we have I here in front. Sine theta. So next time we will decrease and increase that one. So if you decrease, next we have cosine theta, because we decrease it, we increase this one. Each time the sum should give us, the sum of the exponent will give us 3. Now we have 2 plus 1 is 3. Now here if you bring it to 1, the other one should be 2. So we have I square here. We can take it here. We have I square sine square theta. Then the power here now will be 0 and this one increase to 3. So the power of I also here will be I cube and sine cube theta. Now we need to add this coefficient. So we have 1, 3, 3, 1. So 1, 3, 3, 1. 1, 3, 3, 1. Let me shift this to get more space. Unfortunately, let me good. Okay, so we have 1 and here 3. So plus 3. Here plus 3 plus 1. So it is there. Now we can group. We know that I squared is negative 1. So if we substitute this one, of course, if I square is negative 1, I multiply by I here and I there, so this is negative I. So we can group and see that this is cosine cube theta. So this one is negative 1, we can group with this one, minus 3 cosine theta is sine squared theta. Now, the ones with I, you can see plus I, group the terms with I, we have 3 cosine squared theta sine theta. And this one, from here, if you multiply both sides, we have I cube will be negative I. So, negative I, if you factor by I, this will be negative sine cube theta. So now to equal the two, we have cosine 3 theta will be equal to this one and sine 3 theta will be equal to the imaginary part. So what interests us is particular this one. So here we have cosine 3 theta will be equal to this, which is cosine cube theta minus 3 cosine theta sine squared theta. Sine squared theta we can replace it with 1 minus cosine squared theta. So everything is just in terms of cosine. So if we expand this, you can see that this will be negative, negative will be plus 3 cosine cube plus this one will give us 4 cosine cube theta minus 3 cosine theta. So you can see that we have exactly the same result as the one above. 4 cosine cube theta minus 3 cosine theta. 4 cosine cube minus 3 cosine theta. 4 cosine cube minus 3 cosine. Okay, so we can do the same. Sine 3 theta will be equal to this one. So we have already sine cube here. we have cosine square. We can also replace cosine square in terms of sine square and expand. So maybe we can quickly do that. So we also have sine 3 theta equal to 3 cosine square, which is 1 minus sine square theta into sine theta minus 3 sine cube theta. So if you expand this, we obtain, okay, so this one, we have sine square sine theta is negative 3 sine cube with this negative 3. So we have negative 3 become negative 6 sine cube theta plus 3 sine theta. Sine theta, negative 3 sine cube, negative 6. So we have, so if you have one cosine or sine of any angle, twice angle, triple angle, quadruple, and whatsoever, we can use this Euler's formula and Pascal triangle, or we can use just a binomial formula and we get the various result. So we can stop here for this session, and we will continue next time. Thank you so much for your patience and your kind attention. God bless you and see you. Bye bye.